So function dq, we need to remove one value from the q. So what basically we have to do, we have to write a function dq that returns integer. So first we have to declare the value of the variable that is actually integer, because the function returns integer. Then we initialize that data value. Then we check if number in the queue is 0, then we return -1. If it is not, then we actually first read from the array that is representing the queue from the head index, because whenever we dequeue from the head index. And then first, when we have noted it, then we have to move the head index forward. If head index is at 9, we will make it 0 as it is a circular queue. And if it is not, then we just move it one further. And then we decrease the number of items in the queue by 1. And then we will return the data value and function ends. The following procedure performs an insertion sort on the global array, the array that has 10 elements. The following procedure performs the function sort insertion sort on the global array, the array that has 10 elements. Complete the pseudocode for the procedure insert sort. So count will be 1. Procedure insert sort. Since the array is global, we don't have to receive it as parameter. It will be available directly. Procedure insert sort. Declare count as integer, declare counter as integer, declare temporary as integer. Count is equal to 1 while count is less than 10 because the values are 10 in the array. Temporary is equal to the array count. Counter is equal to while count is less than 10, counter is equal to count minus 1. We have to reduce it. While counter is greater than or equal to 0 and the array counter is greater than temporary. The array counter plus 1 is equal to the array counter. Counter is equal to counter minus 1. And while the array counter plus 1 is equal to temporary and count is equal to count plus 1. All right. This is something called decision table. This used to be in the syllabus, now it is no more. So this is obsolete, not in syllabus. These are decision tables. Okay, so we are actually ignoring this question. This is state transition diagrams. A state transition diagram is basically about the state of things when some actions are taken on them, whatever the state that they had may or may not change. So we have to record the action those are taken and resulting states. This is called a state transition diagram. So Anika is designing a computer program. The user controls a character that moves around a virtual world. When the character meets an animal, if the animal's strength is less than 10, the animal runs away. Okay, animal runs away. If the strength is less than 10, then animal runs away. If the animal health is less than 10, if the animal health is less than 10, then animal is caught. Animal is caught. If the animal's strength and health both are both 10 or more, the character and the animal compete. Animal health is greater than or equal to 10 and animal strength is greater than or equal to 10, then they compete. Okay. When the character and the animal compete, when the animal and the character compete, the animal's health and animal's strength and character's health is decreased by 1. So animal health is equal to animal health minus 1. Character health is equal to character health minus 1. So it is also decreasing. This is repeated until one of the following condition is met. The character health goes to 0. Health is equal to 0. The game is over. The animal's strength goes below 10. The animal is runs away. The animal's health goes below 10. The animal is caught. So this is now complete. So this says that if the animal health is greater than or equal to 10 and the animal strength is greater than or equal to 10, then they both compete. If the animal strength less than 10, animal runs away. If animal health is less than 10, animal is caught. If while competing it goes below 10, the health goes below 10, then animal is caught. Animal health is equal to animal health minus 1. When they are competing, their health, animal's health and strength is reducing by 1, whereas the character health is also reducing by 1. So if while competing character health goes to 0, then games gets over. You are beaten. Okay, now this is basically low-level language program. Okay. The table shows assembly language instruction for a processor that has one general purpose register, accumulator, and the index register IX. Okay. So we have got all these opcodes and operand. Let's see if it is something that we have not studied. LDM, load immediate, load direct, load index, load to index register, store, add, increase, compare, jump if not equal, logical shift left, logical shift right, output, and okay. So this is all that is given in the syllabus. There is nothing new. Now we have to write this program. Initialize index register to 0. It means that we are loading to index register, LDR, and what we are loading? 0. So since it is value, so LDR, what LDR does, it loads directly to the index register. LDX character, load the character and multiply it by 2. Now, if you do remember, when we shift left, if we have got 4 bits, let's say 1, 2, 4, 8, and we have 6 in it, and we move it towards left, this will become what? 8 and 4, 12. So it was 6 and now it has become 12. So it is being multiplied by 2. So what we have to do, we have to write L logical shift left 2 times. 1 time, sorry. Okay, so this will be multiplied by 2. Then we have output, we increase the index, we load the count, And then now let's study what it says. An algorithm stores 3-character words. It takes each character in turn, multiply its value by 2, and output the new character. Complete the following assembly language program for the algorithm using the instruction set provided. Okay, so LDT count increase. This will increase the accumulator. Stores back at count, compare 3. Jump if not equal to loop and end. Okay, this is it. So basically there are 3 characters. Ahmad, you can write with a and with 2, but that is doing the same thing in unexpected way. So you can do that. You can do that. But I hope that your examiner would not get it properly. So this is better that we use shifting left and right. If we shift right, it divides by 2 and apply integer to it. If we shift left, it multiplies by 2. So make sure that whenever it is multiply or divide, we should use LSL and LSR. Okay. So that's it. Paper completes. Achha, for you now, for paper 3, you have an idea that you won't have everything related to programming. These papers are heavy because they are paper 4 and they are related to programming only. Okay, so you would have half of your paper from chapter 13, 14, 15, 16, 17, 18 from 6 chapters. So you will have about 75% of the paper 3 from chapter 13 to chapter 17, and then 25% from chapter 18 and 19. 19 and 20, sorry. So that's about it.